Mounting microphones on drones. I think it's
Yeah. So thank you for the introduction, Will. Thank you for having me today. As Will mentioned, my name is Costa from the University of Derby. I'm a third-year PhD student, and today I'll be talking to you about it. It's called Autonomous Acoustical Assessment of. Everything okay, Tony?
You can.
Sorry.
my fault.
Autonomous Acoustical Assessment of Electroacoustic Systems using Unmanned Aerial Vehicles. Why we're doing this project? We're based in the live sound engineering sort of field, and why we wanted to do this project is because the engineers that work in this field, they usually have to work very long hours, and it can be very mentally and physically demanding. So what we wanted to do is to achieve a democracy of sound, is what one of my colleagues likes to puts it. That means delivering the same listening experience to all audience members. And to do that, we need to take multiple measurement points across the venue. That takes a very long time. But what happens is that often the measurements are only taken at the front of house position, and there's very little understanding, or it's usually derived from simulations and very few sample measurement points in the audience areas. There are standards, British standards and international standards related to loudspeaker measurements for maintenance and installation purposes, but I won't be going through all of them because there's too much to cover. So the aim of the research is to develop a practical, efficient, and high-resolution electroacoustical measurement system that provides engineers with an order of magnitude improvement in knowledge of large-scale sound systems, performance in venues, and public spaces. To do this, an array system using high-quality microphone capsules in an omnidirectional arrangement has been proposed to perform the localization of problematic sound reflections. The array will be carried by a remotely piloted drone, and the audio data will be transmitted wirelessly to a base station for analysis. The system will take impulse response measurements to perform acoustical analysis of the room and sound system before the event is happening, so the environment can be controlled. Underlining here before, because we don't want the drone to be flying around when there are people about and cause a lot of harm to them or to the drone itself from unbehaving participants of the audience. And that also, we are not legally allowed to fly the drones within, I think, 50 meters of non-essential participants to the work. So let's have a look at what the research says. What I found so far. We'll start with microphone arrays. And by array, what we usually mean is a system containing multiple microphones arranged to capture sound from the same sort of environment and send it to the same target computer. But what we found so far, maybe some of you are already familiar with the picture there on the left. Most of the microphone array research is based on linear aperture arrays, large aperture linear arrays like you see in the picture on the left, or small aperture spherical arrays like you see in the picture on the right. Both of these cases use electric condenser microphones, analog microphones that are mostly used in beamforming to detect sound sources. And you can see in the images there, they can range from something like 10 microphones, or in the other picture, even up to 144 channels of microphones. But now, with newer technologies, we've moved to use digital microphones, which can be called MEMS, micro electromechanical systems. They are very small, and they can be more power efficient and more noise resistant. Can, but not always, are better than their analog counterparts. The issue that we come across when we are using so many microphone channels is called aliasing, or an ambiguity that may appear at high frequencies due to the spacing between elements. But what aliasing essentially is a loss in the ability to determine the source where the sound is coming from, or also known as the angular resolution of the source. We can calculate this aliasing, but it has different formulas for linear, circular, or spherical arrays, which we'll see in the next slide. In the images here, we have some other MEMS microphones arrays, with large number of elements, with up to 300 channels in the image on the left. This was used in a basketball court field to track the position and the speech of the basketball players. And on the right, we have a sound cam, with 112 microphone channels, and this can map acoustical signals to a visual image taken from a camera to detect sound sources from very quiet sources, even like whistles and stuff like that. So as I mentioned, for the calculation of the aliasing, there are different formulas. There is a basic formula for element-to-element aliasing and used in linear arrays, and this is fairly straightforward. And then the second formula is used in circular arrays. It gives us a bit more resolution. Mainly they cover, they involve the distance between the elements, the speed of sound, and the wavelength of the target sound source. Essentially, what the Riley criterion, which is one of the formulas that is involved in the calculation of the spatial aliasing in the circular array, it tells us that aliasing appears in the first time there is the detection of the 180 degrees out of phase interaction of the two noise sources, or sound sources, not necessarily noise. So, based on these formulas, I tried to calculate what sort of array aperture we should be creating for our drone. And you can see a drone on paper. I still work on paper a lot. How I tried to design the array for the drone. And I think you can also agree with me when I say that 60 or 1.2 meter diameter array is not quite safe to fly around on a drone. And it will cause quite a lot of problems of stability and accessibility of the drone around the venue. So if we look here, I picked in the table some random values related to spacing or frequencies, and then some fixed values that are constrained to the dimensions of the drone we are using. And in the bottom image there, you see recording I have taken of the drone noise, current drone noise that of the drone that we have built without any modifications. And I have plotted the frequency ranges. I don't know if this is very visible on the whiteboard, but I've correlated the measurements and the calculations here to the aperture or element spacing with the frequency that we have. So in the bottom, you'd see the range of the STIPA baseband signal, which is what we will be using to calculate the speech intelligibility of a room. And essentially it's telling us pretty much what is the normal frequency range of human voice within 125 and 8 kilohertz. There's, of course, some frequency harmonics going outside of this range. But in essence, what I wanted to say is that there is no really great solution for the aliasing problem in terms of the dimensions of the drone, because if we would pick something, let's say that goes outside of the main human speech range here, we would need a spacing of 0.085 meters. So that's about, I think, 8 millimeters or 8 centimeters between the elements of the drone. That would fit somewhere right inside the frame itself of the drone, and then we would have issues with acoustical shadows. Now, finally, I won't go through all of this, but if you're interested in calculating aliasing in spherical arrays, we need to account for spherical harmonics. And I think if you want to go through all the math to do this, you would probably need another PhD, so I'm not going to do that today. But the result is that the ground takeaway is that the results that we would see from this circular array calculations are not that far off that you would see, for example, from the calculations of the linear aperture or the circular array. So moving on. When I started a PhD and the idea was to put microphones on drones, I thought first thing, okay, let's have a look and see if there's anyone else putting microphones on drones. And this is the first paper I have read from Hoshiba et al. In 2017. It was the research is based on Nakadai Lab that have published over 400 papers and in DSP in the robot audition, and they are constantly developing the music algorithm that does sound source localization, and they're constantly working on this issue of microphones on drones. But anyway, in the image here, we see from Hoshiba et al. They designed a microphone array for certain rescue operations that is installed on the drone. They have 12 microphones, and they have used the music multiple signal classification algorithm for this sound source localization, which had pretty good results, above 80% in general, and the success rate, detection rate dropped below 80%, when the signal to noise ratio was below 10 dB. What I will mention is that with this array, they did not provide any sort of physical treatment to the noise of the drone itself. So the signal to noise ratio was generally just around that minus 10 dB limit that they agreed. There is a lot of other work on drone audition and drones on microphones on drones or microphone arrays used to detect drones. I added here a few to peruse at your leisure. What is general the case is that a lot of the research is done on microphone arrays sitting on the ground, and they are used to detect the drone of the noise of an incoming drone, or they try to detect and track the passage of the drone over the microphone array and plot that sort of transition. To do the sound source localization, which we probably would need in our case of the measurement of the acoustical rooms of the venues, we would want to track the problematic reflections that might be coming from the ceiling. If you have noticed in that first picture of the arena, there is lots of beams coming and forming around the ceiling. So those can cause some sort of problematic reflections. So what I've been looking at so far in terms of sound source localization methods is the music algorithm, as I mentioned, developed by Nakadai Lab. And in the image there, you see pretty much the latest version of the algorithm presented at the Quiet Drones conference this September from Komatsuzaki et al. And what they essentially have done, they have improved the localization format by removing essentially all the calculations points that were not directly detected sort of into the direction of the higher amplitude sound sources. But the music algorithm unfortunately suffers from sound, as I mentioned, from the signal to noise ratio. And we want to improve that for better accuracy and faster compute time. I would be remiss not to mention that this is not the only version of sound source localization. There are other algorithms and methods for sound source localization and separation. Namely, a couple of them beamforming or ODAS, which is a framework that uses tracking with a particle filter and separation of the delay and some more other methods. It's quite interesting, but it's not exactly what I would be looking into because it's a lot more complicated. And also, the next step is that the sound source localization works better if we manage to do a little bit of noise cancellation in the DSP in the digital world, so we can reduce some of that unwanted noise before we actually improve our SNR. And there's various methods to do this as well with machine learning or deep neural networks or convolutional neural networks. Wang and Cavallaro have quite a good series of papers on this. And another option from using convolutional neural networks here from Ding et al. They used a combination of a microphone array and a camera sitting on the ground to detect the incoming noise of a drone. And I think they, oh no, that's the next paper I'll be mentioning. Now that I have to include the buzzword of this century, AI, there's some new methods to remove noise called from the 11 labs. It's called a voice isolator, and they are very good at removing a voice frequency from background noise. And this could be used as an alternative for offline processing of the data if you want to compute the SEPA or speech intelligibility in the future. But the best option in our case would be some form of an active noise cancelling algorithm that adapts to the different acoustic environments where we are taking the measurements with the drone, because we might be measuring larger rooms that have different or smaller rooms that have different acoustic times properties. So we've been talking about drone noise a lot, but we haven't really exactly explained where the drone noise is coming from. I have shamelessly taken this graphic from Akiwate et al. from DBAC, which is not here today. But it's very, I really appreciate this, his work here, because it explains very well visually where the sound noise sources are coming from in the drones. And we can quantify the two noise sources as either tonal noise or broadband noise. And as you see in the image here, all the sources, the interaction or the standalone sources, they all provide both the tonal and broadband components of the noise. But essentially, to put narrow it down, they have noticed that there is an increase in tonal noise at low blade number and high speeds, and there is an increase in broadband noise at high blade number and low speeds. So there is a kind of like an opposite relation between the two, and if probably the best case scenario would be to find a compromise and get somewhere in the middle, have a design that is somewhere in the middle. But you may see here in the image, there is quite a lot of noise coming from the interaction of the rotor disc of the eddies of the rotor disc with the wing. And also we have found a lot of research has discovered that there is a lower dispersion of noise in the rotor plane. Now, there's a lot of research that has been done in the aeroacoustics prediction area, and a lot of it comes from the military fields and airplanes. But they have given us a lot of formulas and methods to calculate and predict noise and other parameters like thrust and others. Such an example of the equation that it calculates the noise, that predicts the noise, is the Fox-Williams-Hawkins that is based on the computational fluid dynamics data. What you see in the formula there is the general form, and it is used to predict the acoustical, quadrupole, dipole, and monopole sources caused by the vibration of the wing under analysis. Lockhart here in the right, he proposed as well variations for the Fox-Williams-Hawkins equation for 2D, 3D, and time domain and frequency domain calculations. I wish I could have shown you my analysis that I shown on an analysis on my drone, but unfortunately, when I tried to upload my model, ASIS just gave up in 200 errors, and I gave up trying to calculate it. So, enough with the math. Let's go have a look at actually what I have been doing. I built a drone. We have built a hexacopter because why we chose this frame type is because it provides us a bit more stability in hovering, and it has some contingency in case of motor failure, so the drone can land safely by itself even if one or two motors fail. It also provided us with a bit more lift capacity because when the project started, we were not exactly sure what kind of weight we were looking at for the design of the microphone array. As well, the drone has 10-inch blades, 1045 code, because a larger propeller would help us create thrust more efficiently, and it is expected to generate SPL into a lower sort of area of frequency range. And that would be less, but perceived as less noisy, less annoying. The drone size, it also gave us a bit more flexibility in terms of the array design and the battery choice. Overall, the drone weighs about 1.5 kilograms and has 60 centimeters diagonal wheelbase. In the bottom there, you'd see the calculations of the flight time capacity and current draw based on the weight of the battery that we are using. And we have two batteries, but they're all rated for about the same power. Just as a quick diagram of what the drone itself looks like on the inside, the anatomy of the drone, if you will. I won't go too much into the details of it, but essentially what we need to know is that the flight controller communicates with the ground station, and it is powered by a power distribution board. And from the power distribution board, we also power the microphone array. Right. So now that we have discussed at the start a little bit about the actual the digital world noise cancellation, I thought about, okay, if we want to do some sort of treatments to the drone, can we reduce the noise that the drone makes before we have to start doing the digital cancellation of the noise? So I found out there are some methods to reduce the noise. I call these physical noise suppression methods, and I chose three options. The first one is inductive propellers, which is a method of improving the hovering efficiency and reducing the noise dispersion based on the Quanda effect and the Bernoulli's theorem. The second option is inverting the motors of the hexacopter and facing them downwards, so we are eliminating that interaction of the propellers with the wing. And the third option now it's becomes quite popular. I think most of people have seen this Mark Rober video in 2023 from this company called Zipline that have designed this sort of vertically and angularly offset propeller. And in the video, they don't really state the precise measurements, and I haven't found any white paper from the company or anything that they talk about their noise. But what I assumed from the video, looking at the sound level meter he was holding up in the video, is that the drone produced around 60 to 65 decibels at around 10 meters away from the measuring point. Let's have a look a bit here at ducted fast design that I've been working on recently. The design, what I should mention is that, as previously I said, there's a lot of research that has been done, mostly from the military domains, and they have been focusing this aerodynamics research on airplanes. And the dynamics are a little bit different when we're comparing it to a drone, mainly because there is less inflow, and the Reynolds numbers are very different, and the atmospheric conditions where the drone operates are very different. They're not flying nearly as high as normal planes do. But based on the work of Pereira and Hu et al., we can they have tested these design parameters with numerical simulation, CFD, and experiments, and they have concluded that to reduce the noise of the drone and improve its hovering efficiency, we need 0.1 dt tip clearance, dt being the total diameter of the throat that you will see in this example there. The lip radius of the duct should be 13% dt, and the diffusion expansion angle 10 degrees with a diffusion length of 50 to 72% dt. Now, taking these measurements into account, you can see that in the table there, I have calculated according to our drone what these values are. And you see another column in there called constrained. Why is there a column there? Because these values are idealistic. The proposed values are idealistic, where they were testing these designs on a standalone propeller and a standalone rotor, not exactly in a drone that was already manufactured. So based on the constraints of the drone, as in the spatial constraints of the drone, what we have available, I've narrowed down these parameters. You can see, I think from the room you can hardly see it, but on the right side is the profile of the drone duct that I've designed based on these parameters. What I will mention mainly, the tip clearance was narrowed down to 0.3 instead of 0.26 because this is our 3D printer's acceptable tolerance, is 0.3 millimeters, and the duct is 3D printed. And the diffuser length is quite a big problem because it suggests 50 to 72% diffuser length based on the total diameter, which in our case, it would have been 13 to 18 centimeters. You can imagine that hanging a 13 to 18 centimeter duct from the drone arm would not be really a good idea. Or in the other example here, 1.2 times dt. This comes from airplane research, and which was a duct of 31 centimeters, which would be touching the ground. And I think it would be much more difficult to create lift in that situation. So I wrote down the dimension of the duct to what we had available to what we could do with our drone, and that is about 57 millimeters. And again, the same problem due to physical constraints. We have to reduce the lip radius because if we were to have a lip radius of 33 millimeters, as instructed there, as suggested there, they would be overlapping between the motors of the drone. So I had to reduce it, give it a bit of space for so the ducts don't touch and they don't transmit vibration from one to another, down to 19 millimeters. The vane and the diffuse angle were fine. So these are the plots of the ducts that I have designed. I built them in Fusion 360. What I thought after I printed the drone, I've noticed that the inside surface of the duct was quite harsh. It was quite coarse. So I thought that would definitely have an impact of the acoustical transmission and the reflections that are coming out from the drone. But it should have been, it would have been interesting to actually study the effect of this grit and of this coarseness on the acoustical impact. I have already sanded it down and polished it to have a smooth surface. The next I want to mention about the vanes. As we've seen previously, there is quite a lot of noise coming from the interaction of the propeller jet with a static object. So in that case would be the stator vanes that hold support vanes that hold the duct. So I thought, what if we change the way that the ducts, the vanes are shaped? Would that impact the acoustical signature and the aerodynamic performance of the duct? So as you see in the three images on the bottom there, I've proposed three curved vanes and arranged in a symmetrical and asymmetrical method. With the one on the bottom right corner just being an absolute outlier case, just to prove that there is no actual benefit, or if there is any actual benefit, of how does it impact. But unfortunately, I haven't managed to find much research done on this field of curved vanes or asymmetric vanes. The only mention of asymmetric vanes I have found was in an example from helicopter tail rotors that had reduced spacing. They called it sinusoidal modulation of the spacing of the duct vanes. And off the top of my head, I think they said it reduced the noise of the tail rotor by roughly 20%, but don't quote me on it. So this is a topic for further research after the PhD I doubt I will have enough time to cover this as well. Can curved or asymmetric vanes reduce the noise by reducing interaction periodicity and or noise propagation paths? Finally, let's talk a little bit about what I mentioned with the pusher configurations and the offset propellers. This Sharma Atkins paper was pretty much the only one that I found on drone inverted configurations or the pusher configuration. But they suggest that in their model of the inverted rotor hexacopter, they generated 15% more thrust compared to the standard propeller configuration, and it was more stable in hover. And it consumed 13% more energy during flights at higher speeds, but 5% less energy with speeds below 2.2 meters per second, which is quite a good advantage for us. Unfortunately, the paper does not give us good measurements of the noise. They just give us subjective observation that it produced less noise. So we can't really trust them too much on that. But our expectation is that the interaction, the lack of the interaction with the arm will reduce the noise. And also, we should mention that these findings, a lot of the research is done on outdoor drones, and it might not hold indoors where we are flying our drone and where we are testing our drone due to air recirculation and to different Reynolds numbers. And also, one thing a designer would have to keep in mind is that changing the position of the motors changes the center of gravity and the center of pressure that affects the aerodynamic performance calculations of the propellers. Finally, about the offset propellers, there's again very little research I have found online. There's paper here from Musol et al. Also presented at Quiet Drones. And they have tested the different degrees of separation of the blades compared to a reference model. And they have shown that the offset propellers have shifted the acoustic energy into lower frequencies, but they have similar broadband noise and some loss of thrust for the 90-degree separation between the blades, which is they considered that this was not really a win or an improvement, a noticeable improvement over the standard propeller. But you can see in the graph there that this first frequency peak has been shifted down a little bit. So they assumed that the main takeaway from this separation model is that it would have less impact on community annoyance. I believe this is a field that is still worth continuing the research because the vertical offset implications would have to change the calculation of the blade passing frequency, the disc solidity, or the formation of trailing edge eddies, and the noise propagation and more. So let's come around the circle and come back to run microphone arrays again. This is the current diagram of the array that I have proposed. I've started the design based on a Wi-Fi card because we wanted to send the data wirelessly, and the other image that you see there in the center is a multiplexer that takes input from 8 microphones, medium microphones, and sends out output of just a stereo I2S format audio on 48 kilohertz and 16 bits. And the Wi-Fi card communicates directly with MATLAB, where it sends the data on 2.4 gigahertz via UDP protocol for analysis. And the entire system is, as I mentioned, is powered by the 5 volts pad on the power distribution board of the drone. As I mentioned, there's each multiplexer accepts up to 8 microphones, and we can chain up to 4 multiplexers together to form a 32 microphone array system that can be daisy changed. The multiplexer and the microphones offer easy left-right configuration, element configuration, and the I2S, which is inter-integrated circuit sound. So it's the variety version of the I2C communication protocol. It can be programmed up to 32 bits, 768 kilohertz sampling rate. The PDM microphones require a clock, also derived from the Wi-Fi card, and it can go between 7.68 and 6.1 megahertz. I2C can allow us up to 1,000 kilohertz, and the entire current draw of the array calculated, including the Wi-Fi being transmitted at max speed, is roughly around 600 milliamps, or I think for 16 microphones. On the right, you see narrow down a smaller version of the schematic of the microphone array. And in the bottom corner, you see the I2S mode, how the samples are allocated on the clock signal. This is the last bit of math, I promise. This is the plots I have made in MATLAB based on the array pickup patterns. In the first image, number 1, you see the drone simulation and fusion with that I used to try to narrow down and design the array alignment. But you can see that based on the calculations of the aliasing over here for the 60 centimeter, 51 centimeter radius array, we would have aliasing at 350 hertz, which is fairly in the middle of the fundamental frequencies of speech signals, and for an array arranged as you would see in the image here. But in the case of in the bottom here, I've let MATLAB do the assignment of the elements of a 16 microphone array instead of 12 to create this sort of perfect circle arrangement of the array. That would be a lot harder to achieve if we install it on the drone. But this is the sort of pickup pattern that, or polar pattern, if you will, that we would expect for a 1 kilohertz sound wave. Just quickly here, I won't talk too much about the network transmission, but we can get around 40 meters range indoor from the transmission of the Wi-Fi card. And as I mentioned, it's based on an ESP32 and connects to MATLAB via UDP protocol, because while we are using UDP over TCP, UDP does not have a retransmission request in case of a package drop. So we don't lose as much time and audio data fidelity along the transmission. Okay, let's have just a quick look at the results of the experiments that I've run. I've flown the drone inside the Hemea anechoic chamber. Here in this test, in the image, you will see the drone is tethered, but I have flown it untethered after I have learned how to pilot it. And in both cases, I tried to keep the drone at 1.5 meters high, and that took us to about like 70% thrust of the motors. I took 30-second measurements, multiple 30-second measurements, I think over a total of 5 minutes each in the tethered, untethered, and inverted case. The results were quite similar in the tethered and untethered flight. And what we have seen is in the standard configuration, we have about 71 decibels average scale with a 75 dB LAEQ over 5 seconds. Whereas in the pusher configuration, in the inverted configuration, it goes actually on the opposite direction of what the research had told us, and it actually created more noise. So we have 84, we measured 84 dB maximum SPL, but this was because the drone got quite close to the microphone, the recording microphone at one point, and overall we had the 76 dB LAEQ over 5 seconds. So what we see in the plots here on the left upper hand side, we see quite a lot of noise in the lower frequencies. But I assume that happened due to air recirculation hitting the capsule of the microphone. But the interesting thing that we have noticed in the inverted configuration that you would see on your right hand side, there's a strong peak introduced at 5 kilohertz, which I have assumed it has appeared due to the propellers having to drive at higher RPM due to the lack of the interaction of the jet stream with the propeller arm that would have otherwise generated a lower frequency, a lower pressure area under the arm that generates lift. In the end, I would say that I would need a better testing method, but this is what I have available to myself and in the university at the moment, so we'll have to make do. I haven't actually managed to do a lot of acoustic analysis, but for the future, the plans are to do loudspeaker testing using maximum length sequence or swept science stimulus. To measure the room acoustics, we would look at parameters such as RT60, STIPA, or spectral content that we would take from impulse response measurements. And to quantify the drone noise, we can look at overall SPL, sound to noise ratio, or the metrics proposed by Ramos Romero et al., loudness, sharpness, and fluctuation strength that we can calculate using the SQUAT toolbox. And everything will be coming out together into a MATLAB software design that would look similar to that. That is a hearing loss simulator that I have designed in my master's thesis project. Okay. So, just to wrap up, a drone was built to carry a microphone array for acoustical measurements. The noise sources of the drone were analyzed and identified, and noise reduction strategies have been proposed. The current measurements of the unmodified drone show us over 70 dB average SPL, which would have to reduce to improve our SNR for the measurements. We expect that applying the 3 noise suppression methods would reduce the overall SPL by roughly 20%. And this tool could improve our understanding of room acoustics and help deliver better, safer listening experiences to our audience members and to our engineers. The system could also help in maintaining large-scale permanent installation sound systems for public announcements. And the further work, what I would like to improve in the future for the project, it would be very nice to include an AI-based pilot that would perform obstacle avoidance and could navigate by itself to the loudspeakers or set measurement points that we would be able to receive from a 3D model of a venue. Or to design a modular, more adjustable design of the array, because right now it's quite fixed and it is very limited to only this drone. It's not really adaptable and not easy to take apart and put back together. Another thing that we could try to improve is to create a holistic PCB that integrates the flight controller, the power distribution board, or the electronic speed controllers, and or the microphone array, multiplexer, and the Wi-Fi transmitter. That could help us reduce the power consumption, the form factor, and it would help us increase the flight time to take more measurement points. I guess it would be an advantage to have a smaller, more compact design of the UAV and the array, because right now, if we're looking at the 60 wheel base diameter drone and a 1.2 meter array, you can imagine that it's quite heavy and quite unstable. And another suggestion from one of my colleagues, after we discussed about the parameters of the duct requiring a 0.1% diameter of the diameter tip clearance between the blades and the duct wall, that's very hard to achieve by printing the 2 parts separately. They thought, why don't we print the parts together and we just break off the propeller with from a very small piece of plastic from the drone. So we can try to design the duct as part of the drone frame and of the offset propeller in relation or as part of the duct as well. And finally, we could try to, as I mentioned, further investigate the curved thoracometric vane designs. Other applications that I've seen, I would see involving drones with microphones attached to them would be search and rescue operations for disaster cases. In customer interactions, because we have a lot of drones using delivery, so it could be we could try to use a microphone on them and loudspeaker on the drone to communicate with the customer to tell them the order has arrived or whatever. We try to use that for wildlife monitoring for birds or whatever wildlife monitoring the biologists do nowadays. There have been different cases of drones being used for industrial monitoring and inspection for facilities like factories. And I have shown you the image, the sound cam, the visual acoustic camera that detects cracks, for example, in pipes that leak air and affect the engineers or the business. Another example that we could use is for noise pollution monitoring for acoustic consultancy firm. For example, you can imagine if we are allowed to fly the drone outside, if the laws would permit us to try to fly the drones outside event venues while the event is happening to monitor the amount of noise being generated by the event and its impact on the community. And finally, another idea of the drone with a microphone on it would be a personal assistant that you would have seen in this video here, but I couldn't get it to connect to YouTube, and it's quite difficult to get this set up. But essentially, what I have in mind is a drone that is vocally commanded, like take off, follow me, or all sorts of things like this that I imagine would be quite useful for someone like a journalist that is going to take an interview of somebody, and instead of having another cameraman carrying a 30-kilogram camera on their shoulder, you can just leave the drone sit in the air and take the video for you. These are the references for the research for the presentation, and thank you for listening. Questions?
So what microarray design are you leaning towards? It kind of strikes me that, to be honest, you did quite a nice lecture review, but it strikes me that the stuff to do with drone ground arrays, direction finding where a drone is actually a completely different problem to the drone mounted thing. And you showed a few candidate microarray designs, but a bit unclear as to what you're actually envisaging going on this drone, or have you not got that far?
Let's go back then to the array design. So I don't know if you can. Oh, takes a moment to swap. There we go. In the image here, you see these sorts. It's quite hard to see. I'm sorry, but you can see these sort of poles sticking out. This is the current design that we have in mind. It's a circular design of 60 centimeters radius, and the elements are separated at equal distances from top and bottom from each other of 26 centimeters, and they are separated at 60-degree angles between themselves.
And have you thought about the effect of the airflow on the beamforming?
Yes, we have thought a little bit about it. It's a bit hard to see in this image here, but
They all go off.
They all go off.
What I tried was to have to place the microphones at equal distances from the disc rotor, so that would, at least in an attempt to physically put them away from the path of the air recirculation directly from the jet stream. But besides that, we probably would have to account for it in some sort of filter or mathematical calculation of the impact on the beamforming of the air recirculation.
I mean, it strikes me that you'd have. I mean, the only way really to solve this would do a kind of CFD simulation of where the jet goes, and where the recirculation is, and then if you probably ray trace, because anything else is going to be unfeasible. If you ray trace through the CFD simulation to find out that, given a plane wave from a certain angle, where does this actually end up, and what is the action? Because the beamforming is dependent on delays between different light positions, and they won't be what you think they are. As the wave is having its speed increased by the flow. So assuming it flowing down, waves from the top pass through the array faster. Waves from the bottom will go through slower because they're going against the flow. So I mean, I'm no expert, but I would have thought you'd have to practice that in the beamforming would be correct.
Yeah, it's definitely an issue that we will be running into as much as we would like to avoid it. but we'd probably have to, just as I mentioned, do some sort of calculation and filtering for the lower part of the array. And yeah, doing CFD simulations would be very nice, but I've tried before. My laptop could not support the CFD simulation, and it's a bit old now, so it's a work for the future, definitely. That's one you wanted to do.
Yeah, so you comment we can start later.
Yeah.
So what John said about the airflows, where are you planning to use this? Indoors?
Indoors. It's only meant for indoors use. So we are aware that air recirculation would be quite a big problem in this case, which is also causing it caused quite a bit of stability and hovering issue when I was doing the test in the campaign.
Indoors, I assume it's like a large room, like theater size. In that case, well, it depends on the size of the room. You won't have effect on the room from the room, but you're gonna have effect on the setting. You're gonna have your own local or near field loading. I was quite impressed when I saw your presentation because it's a lot of stuff there. So just designing the ducts be a whole project, and I'm not in a PhD project. I'm in a project involving. It's quite challenging. So in your prototypes, you already have the ducts.
Where's the image? Yeah. So I have printed the first prototype that is based on the symmetrical design with fixed that you would see more traditionally. Unfortunately, our 3D printer in the university was not large enough to print the duct, so I had to slice it into quarters and put it back together. And when I did that, it was sagging by quite a lot. So the blade, if you can see on the right-hand side, is cutting through the duct side, whereas on the left-hand side, it's sagging by about 3 centimeters, which is not good. So I glued it all together, and now it's a bit more stable. But even so, I haven't, unfortunately, just tested it acoustically, which is something that I should have been doing this week. But
So you could think of that help. It's not a straightforward answer. In clearance, you said
0.1%.
is that's going to have a lot of effects, and you're going to have some funny thing going on there.
I totally expect. So
Why do you decide? Why do you decide to
to reduce the noise dispersion into the playing field, we try to direct the noise downwards away from the microphones. At least
create some shielding?
yes, to do some sort of shielding. At least that was the thought when I started the project, and then we were still looking at calculating the form of the microphone array. We thought that maybe if we reduce the side dispersion and reducing those side lobes would affect less the pickup patterns of the microphones. And I mentioned that the microphones are omnidirectional, but after doing some testing with them, I think that we probably would have benefited more from a cardioid pickup pattern, so we are less susceptible to that sort of inner circle of the design. Now, I have thought of multiple array designs, including active noise cancellation that uses the two microphones facing away from each other to do the cancellation, but my supervisor tried to pursue me to make me pursue a simpler array design just to get the first prototype out.
I think you said that I think it was your last sentence or something like that. You need something stable.
Yes.
That's true. You need something really, really stable you can track tonal noise. So you want to, if you are doing any active noise control, you need to have that kind of stability. You need to probably monitor RPM, some things to track noise, so you can. They need to reduce all the turbulence. And I think we don't have any experts from the acoustics that we advise on the design. Because you might have some turbulence generated there. I can see the arm of it on, and of these are complete. So but to be honest, it's fairly interesting product. It's quite big now, I guess. But you will need to find a balance between. As you said, you want to have probably larger propellers, the blades, speed slower. Same time you want to control all the turbulence. So it's a very challenging process to find the right design.
Yeah, I agree. It's a difficult process that we would have to make quite a lot of compromises for. We either have to sacrifice some of the aeroacoustic performance and take some losses in power efficiency and thrust generation efficiency if we want to reduce the noise. Sorry, but considering that the drone is meant to be used only indoors for very short amounts of time to take the measurement points, and that we want it to be as stable as possible, we can sacrifice on some parameters, including thrust generation, speed, and drag. Of course, installing the duct will increase the drag, and in some cases, in some of the papers I have read, they are complaining about this as a bad thing. But in our case, it's actually an advantage because we want the drone to be as stable as possible into a single point. So reducing that drag would help us stabilize the drone a little bit.
You looked at helium balloons.
Ha! Thank you for asking. The helium balloon was actually one of the first ideas when I proposed the PhD project. This you would see here in the right is an example of a giant microphone, if you will, or a sampling station from NASA that is hung up by a balloon. But this is 12 meters high. It's 12 meters tall. So you can imagine that balloon, how big it is. So I've done some calculations for the 10-kilogram drone that we have seen in Hyoka et al.'s paper, when I started the PhD, it would take us about 9.5 thousand liters of helium to lift the drone up, and that comes to 840 balloons and costs about 1,500 pounds. It wouldn't take us 10 kilograms, but still, it's still quite a lot of balloons that would have to fill up with helium.
So you wouldn't need that much weight actually. I mean, these things do exist because I've seen them on YouTube.
Mm-hmm. There's some new designs now of what are Zeppelins?
Yeah.
Blimps, I think you call them.
Yeah.
But the range is very lightweight.
Mm-hmm. It's definitely something we can consider in the future. It was something I was considering in the initial designs of the drone itself, but the manufacturing process for it would have been more difficult than what I have done now, where I just ordered the frame and the parts individually online, and I've just put them all together. But it's definitely a good idea. It's something worth pursuing.
The safety. You tell anyone that you want to bring 1.5 with the drone inside a room, fly that around.
That's why we're doing the measurement before the event. I am forced by the ethics committee to be by myself in the room when I'm doing the measurements. So it would be the same case in a real world application. It would be before the event when the environment is controlled and we can evacuate any other unnecessary stuff from the premises. Right, any more questions? Good, thank you.
That's great.
That's all.
Great.
Thank you. Should I leave this here?